Thank you. Hello, everybody. My name is Roshene McCool. I work for Corning Optical Fibre Cable, and today I want to talk about fibre innovations for scale and sustainability. So first of all, let's start by talking about why we need scale. I've selected just a couple of statistics here from a vast array of statistics around network usage. So first, if we look at fixed line users are using 0.5 terabytes per month of data. Mobile users are using 15 gigabytes per month. And on machine-to-machine connections, those machine-machine connections are increasing at 3 times the consumer devices. Now, those machine-to-machine connections might be low bandwidth, but the sheer scale of the number of them is also driving some of the network bandwidths. So, the network bandwidths are increasing across all applications. So whether you're looking at submarine, you're looking at long-haul mobile access, the traffic is increasing in all cases. In this case, what I've used is a source from Telegeography, which is looking at cross-border internet bandwidths. Now the blue line on this graph here, this is the internet bandwidth. The grey and the orange lines are the peak and the average traffic. And both of those lines are rising at about 30% compound annual growth rate. Now this dotted line here is the utilization of the network if we look at the peak traffic versus the available bandwidth. And that utilization figure is round about 45%. It sort of came up a little bit during the pandemic, but it's around about 45%. So what happens if we do nothing? So we're okay, we've got plenty of traffic, we're not going to change anything. Well, what will happen is by next year we will have increased those utilizations by over 50%. And by the time we get to 2025, if we do nothing with that network bandwidth, we will be at full utilization. Clearly, that's not going to help us. And so we need to do something about increasing network bandwidths. Now, many of you will be familiar with this equation. This is the Shannon's equation of total cable capacity. There are two parts to this equation. There's a linear part and a logarithmic part. This B here, this is bandwidth. So we might increase bandwidth by increasing bit rates. We might add wavelengths. We might do some complex modulation on the signal to get that increased bandwidth. And in fact, in many systems, we do all of those things. The other option is that we can increase N. And as a speaker from Corning, as you would expect, I'm going to concentrate a little bit on that today. And then finally, increasing the signal to noise. Now I'm going to touch on these two things very briefly, and then I'm going to talk about this in a little bit more depth. So let's start with increasing bandwidth. Our industry has done really well. This, on the y-axis, this is a logarithmic scale, right? So I had to make it logarithmic to allow it to fit onto the graph. And what you can see is we have increased bit rates over the years. Not only have we increased those line rates, but we've increased the per fibre capacity by a number of ways. We have had wavelength, so we can do wavelength division multiplexing. We can do complex multiplexing schemes like QAM, like PAM4, etc., to get these per fibre capacities up. But what you can see here is that this is slowing down. I mean, I do have to say again, this is a logarithmic scale, but it is slowing down. And we may be reaching that point where we're putting 80% of our effort into that final 20% of gain. Then let's look at signal to noise. Okay, two ways we can make signal to noise better. We can increase the signal, and in terms of fibre, what we do in order to increase the signal, of course, is that we reduce the attenuation of the fibre. And we have made amazing strides within fibre to get that attenuation as low as this. And indeed, we continue to make efforts on reducing attenuation in fibre. The other thing we can do is we can reduce the noise. And one of the ways we do that is by large effective area fibres, which reduce the noise within systems. But as you can see here, we are again reaching a slowdown here. We are putting 80% of our efforts into that last 20% of gain. So now I'm going to talk about increasing the number of fibres in cable. That has a multiplicative effect on the cable capacity. Clearly, the more fibres or pathways you've got in the cable, the more capacity you've got in that cable. But increasing the number of fibres in cable, that is a relative term. So the number of fibres required in a data centre interconnect cable is not the same as the number of fibres needed in a distribution cable within an access network. But they do have one thing in common, and that is that whilst both applications want to increase fibre counts, both applications are constrained in space and want to increase that fibre count within the space that they have. And that means that when I talk about increasing the number of fibres in cable, what I'm actually talking about is higher fibre and cable density. And the number of fibres is relative to the application, but it's the density that matters. Now, density has a benefit in two ways. First of all, if we increase the density, we can take the same amount of space and put more fibre into it, thus increasing the cable capacity of that system. The other thing we can do is we can take the same fibre count and we can go smaller. And that's very helpful in areas such as access networks where the space really is limited and you're really trying to push that fibre out as far as you can into geographical space. I should say here that the fibre design has an impact here, and very recently, in fact last year, Corning released its SMF28 contour fibre. That fibre has two key features which are very relevant to this particular conversation. The first is low OD, and the second is bend resilience. So if you think about low OD, this particular fibre goes down to 190 microns, which is a 40% reduction in cross-sectional area compared to a 250 micron fibre. Now, of course, what that means is you can get more fibres into a smaller amount of space, or for the space you've got, you can get more fibres into that space. Now, we do that without compromising the splicing ecosystems. So this fibre retains the 125 cladding, which is in the conventional G652 fibre, and it also retains the mode field diameter at 9.2, which retains that splicing ecosystem with G652 fibre. Then there's bend resilience. So our SMF28 contour fibre has a bend resilience which is compliant with an ITU-T recommendation G657A2. What that means is that there is a specified limit on the attenuation based on the radius of bend. In an A2 case, that's 7.5 millimeter radius bend and half a dB per turn. Now, of course, that's very helpful as we install networks in operation. But for this particular talk, I want to concentrate on the fact that it's very important for high density cables, because a high density cable environment is actually a fairly tortuous environment for a fibre. There are bends in there, and that bend resilience allows us to get more fibre into a much higher density cable. And indeed, our colleagues, both in our cable business and also in the industry at large, have used fibres like this to get really, really small cables, very, very high density of fibre within a cable. And this is an example of a microduct cable. With these microduct structures, we can put many, many fibres within a very small space. Of course, that has advantages. There may be some of you here who are living this capacity crunch within the network and have an existing network. Well, these very small fibres can be used as overrides on existing networks, or indeed in greenfield installations, we can use these microducts to get really high density of fibres within a very small space. Smaller fibres also have advantages in smaller reels, easier handling, lower freight costs. Now, this effect of miniaturization, so that's to say going smaller in cable whilst retaining that fibre, so going denser within the cable, that has impacts not just on the amount of fibre we can get in the available space, but also on the environment. So Corning has commissioned life cycle analysis. This is an example of a life cycle analysis on our existing standard mini-extend cable. If we take our mini-extend HD cable, which is using those lower OD fibres that I discussed earlier, we can get a 20% lower carbon footprint than in our existing standard cables that use a 250 micron fibre. Now, of course, Corning is also looking at ways that we can further reduce the carbon footprint of our products, and indeed we're embarking on initiatives to get 100% renewable energy over the next 5 to 7 years in many of our manufacturing environments. So let me now talk a little bit about the future. So I've talked about where we are today, but how about in the future? Well, we still need to increase the fibre and cable density. We're not going to stop where we are, right? We need to go further because network demand is not stopping where it is. But I want to add in this idea of not just fibre in cable density, but fibre pathway in cable density. So we're going to start with this particular option for increasing fibre density, which is going even smaller, right? So here in this example, we could reduce this cladding, or we could reduce this coating. We can get down to, for example, 165 micron outer diameter fibre, which allows us to get even more fibre in the cable. That 165 micron is a 55% reduction in cross-sectional area compared to a standard 250 micron fibre. Another alternative is to just put more pathways in the fibre. And so there's a couple of options to do that. The first is a multiple cores within the fibre, so a multi-core fibre. The advantage of that, of course, is that your cable capacity is multiplicative with the number of cores. The second option is to put multiple modes within the fibre, and again your cable capacity is multiplicative with the number of modes. Now that particular option requires the availability of a multiple in, multiple out digital signal processing system. That is not currently commercially available. But so it's a critical enabling component. But once that is available, what you can imagine is that you could have few modes and multi-core simultaneously providing that multiplicative effect. So that's all well and good, but those are pretty radical ideas, right? Because that requires a full change of ecosystem. If you think about the 250 micron fibre that we all know and love, have been using for many years, that has an ecosystem with large-scale manufacturing, with measurement and test, cables, craft training, amplifiers, transmitters, receivers, connectors and splicers. And that's taken 50 years to build up and to reach maturity. And so if we are to go to new radical fibre designs, we as an industry will need to galvanise around a solution and work that ecosystem, develop that ecosystem to maturity, and at a pretty fast pace, because the network traffic is rising at 30% CAGR across all applications. And so we as an industry have a challenge here. Now, this is possible, particularly when problems are real and solutions exist. If you look at this graph here on the right-hand side, Corning have been measuring for a number of years the adoption of low OD fibre. So we've been asking in surveys, are you buying, are you specifying low OD fibre? And what you can see here is that this adoption is increasing, and this has been increasing over time. And the reason this has been increasing over time is because the needs for density in cable have been a real driver for that adoption. And of course, that low OD ecosystem is mature. So whilst we have a challenge in terms of new fibre types like multi-core, like other types of fibre that might help us with capacity in cable, if we can galvanise as an industry, the ability to create that ecosystem is possible. So, in conclusion, network capacity has to increase to meet demand. That is clear. Increased fibre and cable density provides network capacity today. As we start to reach the limits of some of the transmission alternatives to get that bandwidth efficiency, and fibre design is a key enabler of that. And then thirdly, fibre designs of the future will need the evolution of a full supporting ecosystem, and we as an industry need to galvanise around that in order to deliver the fibre and cable capacities that we need in our networks. And thank you very much.
So we need a question from our audience. Any questions? So I do have one question regarding the multi-core. So how come the multi-core cannot do cheaper? So any comments on that?
The multi-core.
The multi-core, right? I got a feedback from including your other like fiber vendors, right? They think the multi-core is very hard to make price like lower compared with single fibers.
Yes. Yes. So there are a number of reasons for that. First of all, we have 50 years of making fibre. So companies like Corning have spent 50 years taking the cost and optimising that manufacturing platform. Multi-core's new, that's going to take time. But there are optimizations that can be done with time and with experience. But the second thing is more fundamental, which is that if you've got one core in a fiber and that one core is in error for some reason, okay, well then you've got some scrap. If you've got 4 cores, any one of those cores is in error and you have to scrap all those 4 cores. So fundamentally, there is a yield question around the number of cores. Now, if you went to, say, some really extreme version of that and you've got, I don't know, 48 cores within a fiber, only one of those cores has to be wrong, and that's that fiber gone. And so that's one of the fundamental things that makes it difficult to get to the same cost points.
And how do you think about the future for this? If you can cost is fundamentally you are not able to get more compatible, right? So what do you think about the future?
I think I am very hopeful that there will be optimizations that support trying to get that cost down. I also think it's about there are some additional things about where we are with efficiency. We've been, in fact, it was in the plenary talk, there was a great graph that kind of went, the cost per gigabit, and it kind of went down like that. Well, we've had a very steep curve downwards on the cost per bit. We may be reaching an asymptote there where some of the electronics cannot get any further efficiencies, and we have to make a step change into things like multi-core.
Okay, we need one question from audience. Anybody?
Hello. So thanks for the presentation.
Yeah.
So still in the question about the multi-core fibers, you said that the multi-core fibers can increase the transmission capacity for the fibers. So compare with the existing multi-fibers. So what's the difference? What's the biggest advantage and the biggest disadvantage for the multi-core fibers?
Yeah. So you said multi-core fibers compared with what?
The multi-fibers.
Sorry.
The multi-fibers.
Right. Yeah. So is the question what's more efficient, multi-core fibers or multi-mode? Is that the question, or multi-core fibers or single mode?
Like the multi-fibers with 12 multi-mode fibers inside of the cable.
Yeah, so the ability to get more pathways within that cable is really what's going to increase it, because the multiple pathways will give you a capacity which is the same as the same number of single core fibers, right? So one multi-core fiber will be the equivalent of 4 single mode fibers. Now we could go lower OD, and that's an option, but that is not giving us the same amount of multiplicative advantage that, say, a multi-core or even few-moded fiber would. Sorry, I hope I've answered your question. It's quite hard to hear in here.
Yeah, I understand. And thanks for the answer. And just one last question. It's about the ecosystem you mentioned about. So you mentioned about that Corning is running to reduce the impact on the ecosystem. So when you mentioned the ecosystem is only about to reduce the density of the cable, or also you thinking about change the material for the cable manufacturing?
So when I talk about the ecosystem, I'm talking about everything that connects to the cable. So connectors, splicers, amplifiers, the manufacturing systems and test systems that are required to build that ecosystem. And that is an industry-wide question, I think.
Okay, so basically it's from every part of the manufacturing process.
It's not just in the manufacturing, it's also in all of the components that fit into a network system.
Okay, Thanks.
Building blocks. Last question. Anybody? Oh.
The last question.
Hi.
So you talked about this new ecosystem, which will be needed, obviously. So where do you think would these new type of fibers be used initially? Would that be more in data center interconnect, point to point, where it might be easier, or in carrier networks, metro core, where it might be more difficult? What's your feeling where the application will happen?
So I think early adopter applications are going to have similar characteristics. The first characteristic they're going to have is they will have a supply of highly talented engineers who are prepared to do something new, go it alone, right? Those early adopter applications will need to be less tied to standard practices and standard ways of doing things. And that means they have to have the confidence to try something new and to make it happen. And the third is they've got to have a really hard driver. And that really hard driver has to be that they are very concerned on fiber exhaust. Now, if I think about the application where that applies today, it's in submarine. So that's, I guess, where I would think it might hit first, but that doesn't mean that's the case. I don't have a crystal ball. But what I would say is I think those have to be the characteristics of early adopters.